and not get lost. Okay, so my talk for today is about Kolasu and LionWeb, and it's an integration story. I am Alessio Stalla. I'm a language architect at Strumenta. I've been working for the company since January 2020, so it's almost 5 years. And besides that, I'm a language engineering enthusiast, and sometimes as a hobbyist, I dabble with Lisp, which is relevant to languages. So in the spirit that that was mentioned before, of trying to be as boring as possible, this will be my agenda, which is really simple. This is not, any kind of research advanced thing, but it's a status of simple of the story of how we integrated LionWeb with our existing technologies. So I will give a quick recap of what Kolasu and LionWeb are for people who are not familiar with them, especially Kolasu, because LionWeb, I guess after this session everybody will know everything. I will talk about why are we interested in this integration, what we want to do, and we'll go over the similarities and differences between the two technologies. So what is easy to map from one to the other, and what proved to be a little more problematic. And then we'll have some time for questions. So Kolasu, first, what it is. It's an open source library that we developed internally at Strumenta. It was initially designed by Federico as a companion for a book he wrote, but then he became basically the main workhorse that we use in our projects. It's a library to support the language implementation on the JVM. It's written in Kotlin and compiled to Java. And it's part of a larger family of libraries and tools that we call StarLasu, where star is just the asterisk. So it's supposed to be the same design philosophy and the same APIs across multiple platforms. So Kolasu is the one for the JVM, and it's the more advanced one of the lot, where all the new developments happen, and then we have ports or variants for Python, TypeScript, and the browser, and C# that are subset of the same concepts. So at its core, Kolasu/StarLasu are libraries to define ASTs and transformations from one AST to the other. And in the context of Kolasu, AST nodes are defined as plain old Kotlin classes. So eventually Java classes, basically. Then we have optional modules for integrated with Antler, so to map an Antler parse tree to an AST and wrap everything in a nice to use API, let's say, that you just call parse and you get an AST. And then we have optional modules for what we call semantic enrichment, so symbol resolution and type computation mostly. And then crucially, we have some modules for interoperability with the rest of the world. So we support exporting and sometimes importing to and from some external formats. And I underline that because that's what we are talking about today. On the other hand, LionWeb, I don't have to explain what it is, but in their own words, it's an ecosystem of interoperable components for building language-oriented modeling tools on the web, and concretely, it's a way of specifying, designing, and storing models that are graphs with a primary containment hierarchy. That was explained very well before, so I won't reiterate. LionWeb is a specification, but it comes with bindings for several languages, including Java and TypeScript and C#, as we've seen, and also a model repository that was the object of the previous talk. So let me go on. So ASTs in StarLasu and models in LionWeb have many traits in common because, yeah, as we said, this is boring stuff. It's more or less the same kind of meta models, the same concepts, but there are also differences. And so we want interoperability, and this is the story of how we achieved it. So before going on, I have to point out that our Kolasu ASTs are not the same thing as LionWeb models, and I'm saying the same thing as in the is-in relationship in an object-oriented language. So early on, we evaluated the possibility to have Kolasu nodes simply extend as a Java class the LionWeb Java nodes, but we decided against that because there are some key differences that we'll see, and also so that we can experiment and evolve Kolasu independently of LionWeb. So this is the story of how LionWeb is integrated with Kolasu as an interchange format. So the idea is that we work within the Kolasu world and then we communicate with the external world using LionWeb. So why we want to do this? Broadly speaking, we want to store and process StarLasu ASTs using third-party LionWeb tools, like, for example, the model repository. But as LionWeb becomes hopefully more popular, the number of available tools will also increase, and we want to be part of that ecosystem. So the idea is that we want to consume some of these LionWeb models as StarLasu ASTs. So the simpler, let's say, use case is when we have an existing AST in Kolasu, we serialize it, we store it in the model repository, for example, or we process it with LionWeb specific tools, and then we reconstruct it as a Kolasu AST, and this all happens, let's say, in a backend of an application. Then we also have use cases where this model will end up in the front end, so using the TypeScript version of StarLasu, but that's not the topic of this talk. And then potentially, but this is not yet something that has happened, but potentially we could also consume third-party models as Kolasu ASTs. So as a case in point, the Code Inside Studio that Federico talked about yesterday is an example of such integration. So we have our pre-existing parsers and transpilers that produce Kolasu ASTs, and then either through a web user interface or a command line tool, we store them in the LionWeb Model Repository. So that means converting them into LionWeb models. Then we get them back from the repository to perform semantic enrichment, case in point, symbol resolution. And so we have to, since our symbol resolution engines work with Kolasu, we have to bring them back to the Kolasu world and then store them back. And then we may want to display them in a web user interface. And all this machinery is necessary because we cannot keep a huge number of ASTs in memory. So we need an we need a model repository to store the models, and we only want to get back the portion of the whole code base or whole mega model that we want to work on each time. So before LionWeb, we had used or started using EMF and eCore for some of the same stuff, but we basically abandoned it because in our understanding it's pretty much limited to Java/Eclipse and XML. So there are ports in JavaScript or Python and using JSON as a serialization format, but they are not official, they are partial, they are unmaintained, buggy, and so on. So LionWeb is very welcome in that space. Another quick point. What I'll present in the next slides refers to the current version of Kolasu. We have another one that is pretty mature in development that will change some of these things, but its adoption even internally at Strumenta is still very limited, so maybe that will be a talk for next year or next couple of years. So let's now see finally how concepts in Kolasu map to concepts in LionWeb, and where there are the similarities and when there are differences. So let's start at let's say at the top of the hierarchy. So we have the concept of the language in LionWeb, which is the kind of node that contains the definitions of concepts in a language and primitive types and enums. And we kind of have the same concept in Kolasu as well. This used to be implicit, so just, you know, in Kolasu we define an AST as a bunch of Kotlin classes, and that's the language. There's no explicit object that holds those together. But already with EMF core, we needed, it became necessary to have something that holds this and lists all these classes. So we just basically kept the same thing. We just called it language to align with the terminology used in LionWeb. Then let's go to the meat of the matter, the concept. So the basic building block for language in LionWeb is the concept, which is a meta node that that defines a class of nodes. So it has a name and the number of features, and what are features we'll see later. So in the present version of Kolasu, this is implicit. We don't have an explicit object that represents a concept. We just use a reflection to derive the structure of the of a node that we're interested in, so which properties are attributes, containments, references, and so on. And to do so, we look at the type and annotations on each property of the node, the property in the Kotlin / Java, the Java Bean sense. Second point, a concept in LionWeb can have an ancestor, so in other words, and can implement concept interfaces. So in other words, LionWeb supports traditional object-oriented style inheritance. Kolasu naturally supports inheritance because node classes are just Kotlin classes, so we have Kotlin / Java style inheritance. So from all that, we can conclude that, okay, Kolasu doesn't have an explicit representation of a concept, but it has all the bits needed to map to a LionWeb concept. This I will gloss over, and maybe we can return to this if we have time or if a question pops up. So let's move to features. So a concept has the name and has a number of features. These can be attributes or containments, as we've seen, or references. Attributes hold values of primitive types and cannot have multiple values, so can't be lists. Containments are the primary hierarchy, the shape that gives the tree shape to LionWeb models, and then there are references that can point to nodes in other nodes in the graph, and both containments and references can be multi-valued or single-valued, so 0, 1, or n. In Kolasu, we have basically adopted the same terminology. So how does each type of feature map? So in Kolasu, we basically don't restrict primitive types in any ways, besides forbidding them to be a list. So everything that is not a node or not a reference is a primitive type. In LionWeb, there is a restricted number of built-in types. So if we want to put in our Kolasu AST some type that is not among the ones that are built in LionWeb, like strings, numbers, basically, we have to use an extension point and provide a custom serializer and deserializer, on the other hand, to process this custom type. Containments in Kolasu, a containment is just a property whose type is a subtype or node or a list of such elements. Nothing special with that. And references in Kolasu, we have the concept of a reference by name, which is an object that has a name, which is basically a key used to resolve a reference, and it has a pointer to the referred object that initially is null, potentially, and then will be eventually resolved during semantic enrichment / symbol resolution. So they're just references in memory, basically, in Kolasu. So how do we map all of that stuff, particularly references, to LionWeb? Well, first we have to discuss a difference between a design difference between Kolasu nodes and LionWeb nodes, which is the key difference and the key issue that we had to overcome in integrating the two. So Kolasu is designed assuming that all AST nodes are in memory, at least conceptually, while LionWeb is designed around the idea that not all nodes are necessarily loaded in memory at the same time, or even come from the same file or same repository, same database, etc. Also, in Kolasu, typically AST nodes are created as the result of parsing source code or transforming from another AST. So basically, they are all derived models. And while in LionWeb, nodes are designed in a way that they could be authored using a projectional editor, so Fern or MPS. So nodes may have an identity of their own. As a consequence, all LionWeb nodes have an ID. Kolasu AST nodes don't have an ID. And so we're converting from Kolasu to LionWeb, we have to provide an ID. And let's get back to references. When converting Kolasu references into LionWeb ones, we basically go through the node ID. So we transform memory pointers, memory references into indirect references using node IDs. I will gloss over the ID strategies because I don't have much time, but we have basically a way to assign the IDs that can use semantic information in the nodes when it's available. So think about like a Java class is uniquely identified by its fully qualified name, name plus package name, and maybe the Maven coordinates if you want to support the notion of having multiple versions of the same class. And some other nodes don't have such a semantic ID available, so we can compute an ID as the path from the closest node with the semantic ID. And that means that the root of, at least the root of the AST must have a semantic ID, which is not always the case, but we can sort of cheat because we can generate a synthetic node that represents the parsed file. Let's say could be its ID could be a path or a URI or a checksum. So we have a way to give a semantic ID that is really not semantic in the sense that it makes sense in the model, but it's a synthetic node generated to provide an anchor point for other IDs to be derived from. Kolasu doesn't term partitions, so we only use them when talking with the LionWeb model repository, and that's just it. And additionally, Kolasu has, or StarLasu in general, has additional types of objects that are not AST nodes. So far we have talked about transforming just an AST into a LionWeb model, but an AST in Kolasu often comes with additional support objects. So we map those to either custom primitive types or special nodes, and let's briefly look about those. So we have the concept of a position that represents the the allocation, a portion of the source code, typically where the node has been parsed from. So a position is a couple of points that are defined as line and column. So this is conceptually structured data. So the trivial, basic, naive idea would be, okay, let's make those into nodes. But nodes aren't cheap in LionWeb because every node has an ID. And in Kolasu, basically every AST node has a position. So we would have to provide 3 extra nodes, so 1 position and made of 2 points for each AST nodes. And when an AST is made of hundreds of thousands of nodes or millions even, that's just not gonna scale. So we represent positions as a custom primitive type. We have also the concept of the source that represents where a node comes from, like a source file or a URI, but we don't persist that information into LionWeb. We may use annotations in the future, but we haven't use for that. And we have the concept of an issue that are diagnostic messages, and we represent those as custom nodes because they are just a limited number of parse errors or semantic errors or whatever. We can also store tokens in LionWeb because we use them on the client to drive syntax highlighting. And again, a token conceptually is a small piece of information that could be encoded as a primitive type, but tokens are a list. We don't have a single token, we have a sequence. So making them into nodes, as I said, are not cheap. So we cheat a little and we represent the list of tokens as a single primitive type that then we parse into something that is a list. And then we have just a holder node that we call parsing result that just puts all this information together, and it's just a node. And that basically concludes our base integration. So how we map from ASTs to models. We have other advanced features that we don't have the time to talk about. So we have, of course, a client for the model repository that is Kolasu native. So you can say persist Kolasu AST or get back Kolasu AST. And of course, it's based on top of the existing LionWeb native client that is part of LionWeb Kotlin. We have support for proxy nodes. So when you load stuff from the repository, you can cut the tree at some point and keep a proxy node there that you will load at a later time. And then we have a bunch of command line tools and Gradle tasks to generate either LionWeb meta models from a Kolasu, LionWeb meta model from a Kolasu AST or vice versa. So let's wrap it up. Kolasu and LionWeb have enough similarities between them, so it's sensible. It's not crazy, and it's a crazy idea to use LionWeb as an external format for Kolasu ASTs. Some differences exist, especially around node IDs, as we've seen. So some extra non-complexity, unforeseen complexity is needed. But nonetheless, we could use Kolasu and LionWeb together successfully in our Code Inside Studio tool. So these differences exist, but they are not a showstopper. Thanks. If you have questions.
Time for questions. Are there questions?
Hi, thank you for your presentation. So how does this bulk command to the model repository work? Is it guaranteed that all models are stored? Or it can happen that, I don't know, it stores half of the models, something happens, breaks, and the other half is, not stored.
Okay, so
is there a rollback mechanism?
So the question is whether the bulk APIs of the model repository are like transactional. So if it's like either all or nothing, or if it can happen that only half of of a model is stored. I'm not maybe the right person to answer this, so I will delegate to the LionWeb repository people, but I know that it's based on a relational database that is Postgres, and which is transactional, so I suppose that's the case, but yeah.
Either you succeed or nothing happens.
Okay, so it's transactional.
Okay, so you're parsing code, building AST, and putting that to a LionWeb repository. And there you mentioned yesterday you were testing it 1 million of nodes for large code bases.
Yeah.
I was wondering if you're trying to process that code base, like from the LionWeb repository, what's the workflow? Do you run your tools on the endpoint, fetch everything on the client side, do the processing and returning back, or there are maybe some in-repository support for some heavy operations like finding patterns or something like that?
Okay, so the question is, we put large models in the repository, and then we pull them out to process them, but is there some features in the repository that we could use to like run processing directly in the repository, like queries or finding patterns? Well, as far as I know, there is no such feature presently in the repository, except some specific features that, like, where you can ask, like, give me all the nodes of a certain type, for example. But this is not the main reason why we do things the way that we do. It's also because our tools were born around ASTs, so we already have logic in place. We already have tools in place that know how to deal with these ASTs, but the problem is just that on large code bases we cannot simply hold everything in memory. It doesn't scale. So we have adapted our semantic enrichment tools in a way that they work on a one AST at a time. So we pull an AST from the repository, we try to resolve references, and when resolving references will point to other nodes in the repository without necessarily downloading everything and doing everything in memory. That way, yes, we still have to get the model, modify it, and store it back. Maybe when we'll have the Delta API, we will be able to just store the modified references, but now we can't. But we don't have to download the whole repository in memory, otherwise it wouldn't buy us anything to have a repository. So yeah, I hope that answers your question.
Let's thank the speaker again.
Okay, thanks.